Although Dr. Ananda Coomaraswamy's early allegiance to geology is largely overshadowed by his later contributions to art and philosophy in the early 20th century, his pioneering geological and mineralogical endeavors in Ceylon are not to be forgotten. The Geological Society of Sri Lanka duly recognizes his early geological work and pays tribute to him by awarding the Ananda Coomaraswamy Medal to a geoscientist who has made outstanding contributions to the advancement of geology of Sri Lanka and geosciences in particular. The Geological Society of Sri Lanka has gathered here today with its invitees to felicitate one such great geoscientist who will be adorned with the prestigious Ananda Coomaraswamy Medal. To begin the proceedings of the event, please rise up and sing the national anthem in unity and harmony.
Sri Lanka Mata, Upper Sri
Thank you. The ceremonial opening of the session will be denoted by lighting the traditional oil lamp. The following invitation goes to the following dignitaries to participate in this important event. Dr. Upul Premaratna, the President of the Geological Society of Sri Lanka, Dr. Jagath Gunatilake, the recipient of the prestigious Ananda Coomaraswamy Medal, Professor Terence Madhujit, the Deputy Vice Chancellor of University of Peradeniya, Professor A. Pitawala, Director, Postgraduate Institute of Science, Dr. Udeni Amarasinghe, Head of the Department of Geology, Professor Ananda Coomaraswamy, Acting Dean, Faculty of Science, and all the past recipient of prestigious Ananda Coomaraswamy Medal, and representation from the Geological Society of Sri Lanka, one member from the GSSL, please. I cordially invite you all to take part in this important event. This invitation is to Professor Balasuriya, who is the nominator of the Ananda Coomaraswamy Medal. Thank you very much. It's my pleasure to invite the following dignitaries to take their seats in the head table now. Dr. Upul Premaratne, the President of the Geological Society of Sri Lanka. Dr. Jagath Gunatilake, the recipient of Ananda Coomaraswamy Medal. Professor Nanda Balasuriya, the nominator of the Ananda Coomaraswamy Medal. Dr. Titus Kure, Secretary, the Geological Society of Sri Lanka. Please take your seats in the head table. Thank you. To welcome the attendees of this event, I cordially invite Dr. Upul Premaratne, the President of the Geological Society of Sri Lanka, to the podium.
Good afternoon to all of you. So, on behalf of the Geological Society of Sri Lanka, I take this opportunity as an honor to welcome the following dignitaries and special invitees for this prestigious event. First, I would like to welcome former Ananda Coomaraswamy Medal recipients for this occasion. and Dr. Jagath Gunatilake, the Ananda Coomaraswamy Medal recipient today, for which we have gathered to witness his receiving of the award and his valuable findings through his oration. Then the Executive Committee of the Geological Society of Sri Lanka and Vice Chancellor, Deputy Vice Chancellor of the University of Peradeniya, Professor Terence Madhujit. You are also warmly welcome, sir. Director, Postgraduate Institute of Science, Professor H.M. T.G.A. Pitawala. Welcome, sir. Head of the Department of Geology, Dr. Udeni Amarasinghe. Professor Nanda Balasuriya, the nominator of the Ananda Coomaraswamy Medal recipient today, Dr. Jagath Gunatilake. And the following special invitees, Mr. and Mrs. J.J. Ratnasiri, former Secretary, Higher Education, Engineering Nihal Rupasinghe, former Secretary, Megapolis, and Professor Kapila Gunasekara, former Vice Chancellor, Dr. and Mrs. Tilak Siambalapitiya, consultant, Professor Upul Disanayaka, former Vice Chancellor of the University of Peradeniya, Professor Sarat Abeko, former Vice Chancellor of the University of Peradeniya. You all are welcome, sir. And all the other special invitees, students, ladies and gentlemen, and those who are joining us online. Please bear with me if I have overlooked any of your names. I have a long list, so you all are warmly welcome and to this event. Thank you very much.
Thank you very much, Dr. Upul Premaratne. As a tradition, the Geological Society of Sri Lanka presents some reminiscence of Dr. Ananda Coomaraswamy in a short video presentation in his honor and as a tribute to him before awarding the Ananda Coomaraswamy Medal. Let us pay our respect to Dr. Ananda Coomaraswamy by appreciating his legendary contributions to Sri Lankan geology.
Geological Society of Sri Lanka is honored to award the prestigious Ananda Coomaraswamy Memorial Medal to Dr. Jagath Gunatilake in recognition of his significant contribution to uplift the geology of Sri Lanka.
From Kurunegala is the eldest son of the Gunatilake family. He had his primary and secondary education at Malideva College, Kurunegala. Jagath Gunatilake entered the Faculty of Science of University of Peradeniya in 1984 and graduated with geology special degree, obtaining the only special degree first class awarded by the Faculty of Science, University of Peradeniya in 1990. He joined the Department of Geology as a temporary lecturer in 1991 and assumed duties as a probationary lecturer in 1993 while carrying out his postgraduate studies in Engineering Geology at AIT Thailand. After completion of his M.Sc degree with excellent performances for the research study on the reservoir leakage problem of the Samanlava Hydro project, he taught soil and rock mechanics, engineering geology, and field geology for undergraduates. Since his second year of undergraduate studies, he was fortunate to have been trained as an engineering geologist under able guidance of late Professor P.W. Vitanage, who is the founding father of the Department of Geology in University of Peradeniya. Jagath Gunatilake joined the Samal Level Hydropower project as the engineering geology for Japanese contractor Kumagai Hasamama Kajima joint venture while studying as a final year undergraduate during 1988-1990. After graduation, he continued to serve the project until the impoundment of the Samal Level Reservoir. Thereafter, he joined with the international training program on deep sea mining and protection of the environment attached to the Berlin University in Germany, conducted by the International Seabed Authority. He obtained his PhD in geotechnical engineering from Saga University of Japan for carrying out research on the mechanism of landslide under Mombusho Scholarship awarded by the Japanese government. Dr. Jagath Gunatilake is an eminent engineering geologist in Sri Lanka and has served many development projects, including Samal Level, Upper Kotmale, Moragahakanda Kaluganga, Umawaya, Gin Nilwala, Upper Alahara, Kandy Tunnel Project, Norton Bridge Reservoir, New Lakshapan Tunnel, Mausa Kale Dam, Kaluganga Dam Site and Tunnel Trace, 2 tunnels of the proposed Ruwanpura Expressway, Talpitikala Tunnel, etc. immensely contribute to the national development of Sri Lanka. His great contribution to the Umawaya project as the chairman of the expert committee appointed by the president when it encountered an unprecedented tunnel leakage disaster in 2014 has been commended by authorities, geological community, and the project contractors. His contribution to accurately identify the potential leakage location in remaining part of the head-trace tunnel was recommended. His contribution to identify the severe leakage which exists over last 30 years in Samalna Reservoir and to find solution to control and arrest it was commended by the authorities and has given a great reputation to the geologist. Out of his attractive teaching always involved with practical experience of geological problems of ongoing and past development projects, and his students and colleagues had excellent opportunity for the advancement of geological knowledge and skills in handling difficult engineering geological problems. He was leading to gather all geologists in Sri Lanka for the effort of a rapid landslide investigation in 2004, when the entire hill country of Sri Lanka experienced an unprecedented landslide disaster with over 2,600 landslides. The operation professional combined, which connected geologists, engineers, and all relevant government organizations, was well coordinated by him and brought the profession of geologists as an extremely important entity in the country with the successful completion of 4 weeks program, giving a great relief to the affected community. Dr. Jagath Gunatilake has served as the head of the Department of Geology, Chairman Board of Study Earth Sciences, and coordinate 2 M.Sc programs in GIS and remote sensing and Engineering Geology and Hydrogeology at the PGIS, effectively helping the advancement of knowledge of engineering geology, GIS and remote sensing in Sri Lanka. The contribution of Dr. Jagath Gunatilake by designing GIS and remote sensing M.Sc program for the first time in Sri Lanka was extremely successful. The 12 batches so far completed had more than 50 students in each batch. State-of-art GIS and remote sensing laboratories he established in the PGIS and in the Department of Geology is commendable. He managed to get this assistant to several international institutions and universities as foreign collaborators to fill the gaps of required resource persons. The short courses series on GIS and application has become very popular among almost all the sectors of government and non-government organizations in Sri Lanka and abroad. And he has completed 128 short courses on GIS and remote GIS and application, making it a record. His contribution of supervising undergraduate and postgraduate research studies related to the related to advancement of geology, introducing emerging technologies of GIS and remote sensing, especially the application of high-resolution drone technology for geological investigation and effect siting wind turbines, solar park, etc. is commendable. His untiring effort for grabbing opportunities to develop and expand knowledge of geologists in other disciplines such as developing renewable energy as geothermal, solar and wind power are remarkable. He has supervised over 280 postgraduate theses, including 5 PhDs, 6 MPhils, and over 200 M.Sc theses. He always encouraged his students to carry out their research studies focusing on the geological problems of the ongoing development project and to make scientific publication leading to the advancement of the knowledge of geology of Sri Lanka. He has over 130 research articles published in international journals, peer-reviewed journals, and presented as conference proceedings. Dr. Jagath Gunatilake was the president of GSSL in 2005 and has served as vice president, secretary, treasurer, editor, and committee member during last 33 years. He has also served as the president of Geoinformatics Society of Sri Lanka in 2006. He also served as a chairman of the Educational Committee of IGSL in 2020 to 2023. He was taking the lead in teaching field geology to undergraduate of the Department of Geology. During last 30 years, he reintroduced field camps in 1992 to ensure that graduates will have appropriate teamwork experience in field geological mapping. With the assistance of the academic staff Department of Geology and the professional geologists from GSMB, NBRO and CCB, he successfully conducted field camps at Moragakanda, Samalawaba, Kaluganga, Umawaya, Ginnilwala and Kandy Tunnel Trace and gave extensive experience in geological, engineering geological, structural and hydrogeological mapping to his students and colleagues. He played the leading role in establishing a new engineering geology laboratory at the Department of Geology and the Soil and Rock Mechanics Laboratory at the PGIS to provide a student with hands-on experience on soil and rock testing, foundation investigation, etc. Dr. Jagath Gunatilake has received many awards, among a Presidential Award for Scientific Publication in 2010, NRC Merit Award for Scientific Publication in 2004, and Sasred Award by the NSF in 2016. Dr. Jagath Gunatilake has been actively engaged in various university committees. He was serving as a director of the Extreme Sri Lanka Japan Center, and he also has the deputy director of CES. Through this position, he continued his spearhead initiatives that foster academic collaboration and promote environmental consciousness. Recognizing the extensive academic accomplishment and scholarly eminence, combined with the multifaceted leadership and his unwavering commitment to the advancement of knowledge and shaping the future of engineering geology, GIS and remote sensing, the Geological Society of Sri Lanka has awarded Dr. Jagath Gunatilake as most prestigious Ananda Coomaraswamy Medal in 2022. Thank you.
Thank you very much, Professor Nanda Balasuriya, for that elaborative narrative about Dr. Jagath Gunatilake and why he deserves to be adorned with this prestigious Ananda Coomaraswamy Medal. He has made remarkable achievements in his career as a geologist. Let us now see significant milestones of his journey in another video. Thank you very much. We have come to the pinnacle of today's event. May I now invite Dr. Upul Premaratna, the President of the Geological Society of Sri Lanka, to the floor. Dr. Jagath Gunatilake, while congratulating you on your great achievement, may I respectfully invite you to the floor also. The President of the Geological Society of Sri Lanka will now decorate the recipient of the Ananda Coomaraswamy Medal for the year 2022. Ladies and gentlemen, please give a big applause to Dr. Jagath Gunatilake. Thank you very much. Congratulations, Dr. Jagath Gunatilake. May I now request the members of the head table to take their seats back in the audience. Over 35 years of contributions to national development of Sri Lanka through engineering geology of dams and tunnels will undoubtedly be an interesting saga. We are eagerly awaiting that narrative. Dr. Jagath Gunatilake, with utmost respect, I invite you to deliver the Ananda Coomaraswamy Memorial Oration.
Good afternoon, everybody. Thank you very much, Professor Balasuri, for giving a descriptive introduction, and also I have to be very much thankful to the past recipients of the prestigious Ananda Coomaraswamy Medals for electing me for awarding this medal for 2022. And I have to be very much thankful to you all for being here with us to share this happiness, of course. Right. So, my topic for the oration is over 35 years of contribution to national development of Sri Lanka through engineering geology of dams and tunnels. First of all, I have to pay my gratitude to our great guru, late Professor P.W. Vitanage, who introduced the subject of engineering geology to us. So as the background, I have to mention that majority of the dams, tunnel projects in the world are successfully operated without any engineering geological problems. Some have been abandoned during the feasibility stage itself. Some have been constructed and operated economically despite the continuous engineering geological problems. Some projects have been failed to serve the intended purpose with unsuccessful mitigation measures and became uneconomical. However, some dam or tunnel projects are operated economically after successful remedial measures. So there are examples for all 5 categories of dam tunnel projects in Sri Lanka. This oration is lined up with 4 selected recent dam tunnel projects with their engineering geological problems and successful solutions. Samanalavawa, Umawaya, and Kandy Bypass Tunnel, and Gingnillala project, and so on. So I'll begin with Samanalavawa Dam, Samanalavawa leakage problem, and so on. So Samanalavawa Dam is constructed in Belihulloya at the confluence of Belihulloya and Walaveganga. And the powerhouse is located down there. Actually, power intake is about 6 kilometers away from the dam and starting from upstream of Walaveganga. And low pressure tunnel brings the water up to Kapugala, and along the penstocks, the water is brought to power generation at the power house. So in Samanalava Dam, of course, there were a lot of problems with the right bank. All others, dam itself is very safe, whereas right bank had a big problem, because actually Samanalava Dam has the highest or longest history in investigations, field investigations since 1954. So large number of nations, Australians, Russians actually began with the investigation. They have done a very elaborative study, and several times this Samanalava Dam project has been abandoned due to the several problems that exist on this right bank. I remember sometime that Russians have recommended to construct a cement factory just next to Samanalava Dam if to fill the highly pervious ground on this right bank. So several times it has been abandoned and rejected, and anyway in 1987 again the Japanese company Nippon Koi came to the front, and they started to bring the project on the ground. So they had many difficulties, but I would say even today the Samanalava Dam project is functioning with very high profits, even despite the leakage problems and so on. So here, this is the initial construction made, diversion tunnels, and then primary coffer dam and main coffer dam, and the main dam was to construct somewhere here. So these Walaveganga and Belihulloya, this is the confluence. So during the floods of Walaveganga, there is a cavity, huge cavity, crystalline limestone cavity. So water used to go into that cavity when the flood water comes over there. So this water goes throughout the right bank, and it extends up to about 2 and 2.5 kilometers upstream of Walavei, because the Walavei river level at this is exactly maintained as a flat groundwater table within the vast area. So this is a 100-meter high rock-filled dam with central clay core, and this is the clay core at the center. And after completion of the dam, actually 9 days after completion of the after impounding of the dam, initial signs of the leakage appeared at the downstream side, somewhere here. Later, in about 8 months later, huge disaster, huge water burst occurred with the, at the downstream of the right bank of about 250 meters downstream of the dam. So this is the place, amount of water leaks and leaks coming out from a fault, through a fault structure. So this is the place where this water burst was occurred. So this is the right bank extending for about 2.5 kilometers upstream with this highly porous material. So this is the recent drone survey carried out. So initially the dam had the idea of having grout curtain along the dam axis and come up to here. But later on it was encountered that this area cannot be watertight, cannot be made watertight because of the huge cavities, marble cavities existing there. So that's why designers have changed the grout curtain direction, and they have diverted it like this, about 2.3 kilometers long additional grouting adit. So for that, to construct that, there were 2 access adits. One is called adit G from upstream side, and from downstream side adit E. So from there they excavated on both sides, and the grouting tunnel or grouting adit was completed later on. And when we talk about the right bank of the dam, so there are some areas. Later on with the investigations, it has been found that these are the boreholes. These red dots indicate the boreholes which are very closely responding to the river level, Wallaby river level at the dam site. Whereas these blue dots indicate no response to the river level. So that means this area has no significance for the leakage. Then it was named as area A, while this area was named as area B because of several special reasons. In area A, the calcium carbonate in marble rock exists with the rock band, exists as fresh rock, fresh minerals and so on. But when the same marble band or crystalline limestone band is extending towards the area B, none of the calcium carbonate mineral remains there. Everything is dissolved, and instead of calcium carbonate, highly pervious ground is there. That pervious nature is there. That's the remarkable difference between area A and area B. This area B extends, as I mentioned, 2.5 kilometers upstream of Wallaby. Not only that, there are some prominent fault zones. So these are a very prominent feature of a fault zone as fault breccias. Fault breccias can be observed while the adit or grouting adit was excavated. Several such features could be seen. So during the impounding of the reservoir, at the beginning, almost all the boreholes, about 35 boreholes constructed on the right bank in area B side, they responded very similar to the river level. So they increased their water level exactly as the river level or reservoir level, despite they are in the upstream side of the grout curtain or downstream side of the grout curtain. So there is no difference between upstream and downstream grout curtain. So it rose until the 22nd October in 1992. Yes, and there, all of a sudden, actually everybody was waiting that something should happen. So water level in the reservoir is rising up, water level in the entire right bank is also rising up in the same way without any difference. So everybody was expecting something should happen at any time. So finally, that October 22nd, that water burst occurred, and all of a sudden the right bank water table was dropped by about 20 meters, and later on it was recovered some. But again, all these boreholes show very close response to this reservoir level with about 10-meter difference. 10-meter difference. So we have proposed actually my master's study also was on this Samanala leakage problem when I was in AIT, and so there are various approaches have been made in the research study, and later on geological mapping and reviewing of the existing literature and everything and so on. And one thing has was found that one adit G, which was an excess adit constructed from upstream of the reservoir to the grouting adit, has been left untreated. With, only this part has been blocked. Concrete plug has been placed over there. So rest of the adit has not been treated. But most of the engineers and all the experts had the idea that this tunnel has been lined, and there is no provision for seepage through that. Actually, the impermeability of the reservoir is mainly due to the saprolite blanket along the reservoir banks. That is due to the clayey nature of the saprolite blanket. But at this particular location, this saprolite blanket is drilled and made the passage through the adit to the right bank. So water can easily go through that, and within the through the fractures, joints and folds along this adit, water can go inside. Not only that, there are some strange features encountered at the upstream there. Some fishermen, they have seen some vortex are developed. So some sinkholes have been developed far away from that dam site and so on. So they were identified as sinkholes. So this is my master's thesis. There it is very clearly mentioned about the potential leakage through adit G. And it was concluded that the passage through adit G, abandoned access adit, may facilitate considerable contribution to the main leakage, as it can recharge the groundwater. And also, apart from the passage through adit G, there is unlikely to exist a major ingress point rather than the ingress zone and so on. So it has been clearly identified, and later we have tried to make a hydrological model for the right bank and the reservoir. So this is the reservoir, and this is the right bank. This is the right bank grout curtain. This is the grouting adit. This is so-called adit G coming up to the adit, grouting adit, but it has been blocked or plugged. Concrete plug is placed only at here. The rest is open. And in the within the right bank, it is just like a honeycomb. So there are a lot of highly pervious aquifers, very well interconnected to each other. That's how, when the reservoir level is at certain elevations, all the boreholes made for these aquifers showed the same piezometric level. And some of these aquifers are connected below the through passages below the grout curtain as well. But we can assume that grout curtain is successful, but the practicability is only 100 meters below the grouting adit. But the folds, deep open folds, still continue even beyond 100 meter depth. So several statistical analysis on this large, tremendous amount of data on this piezometric data available for the last 30 years, and they have been analyzed and it has been found that first burst and the second, actually when the water was raised in the reservoir, it was the burst. Second burst also occurred in 2006. Just after that, the difference between the reservoir level and the right bank water table was increased. That means hydraulic head was reduced. And yeah, this shows the remarkable, distinct 4 events during the history. So this is the very beginning, when the reservoir was impounding in 1992. All of a sudden, water burst occurred and water level reduced on the right bank. These borehole levels. So later on, with the second, actually, full supply level was reached there. But during this time, during this 2006, the second water burst was occurred, and again, the water level in the right bank has been reduced. So this is how this is changing, and it has been found that although they have reduced the water level in the right bank, gradually it again increased because of the results of this 22-23 data. We can see, unless we do some mitigation measures to stop the leak or control the leakage, there will be another water burst and so on. So during the recent studies, some automated network for measurement of piezometric levels have been installed. So piezometers and pressure gauges, and the boreholes also were provided with automatic pressure gauges, so that frequent, even 5-minute interval, we can get the water level data or piezometric data. So this is the added G, so-called added G that has been unlined. So all these brown areas indicate highly to completely weathered rock, almost soil, with open joints and folds. This is how somehow the designers and the experts who have worked on it have just neglected it. That's how it indicates very highly open joints or folds are there. Actually, these are two-fold zones which have been encountered during the excavation of that adit. So this has been treated only at 2 locations, either from here and here. This yellow color shows shot-treated surface. All other areas in the adit G is left untreated. So this is the way geological maps have been prepared for that adit G. You can see only the chain H, right? So all these are open folds or fractures with highly to completely weathered rock. So that's how this adit G was considered as one of the major ingress of the water into the right bank. So that not only that, these sinkholes also paved way for the seepages. So I'll show you that is considerably less. So this is the place where very recently, about 2 weeks back, we have done some dye test, or divers were deployed to see whether this adit G portal is still open or closed and so on. So this is the sinkhole, one of the sinkhole. So what will happen if sandbags are placed from this side? Soon after sandbags are placed, water just go into that, sink into the sinkhole. So this was exposed in last week, 2 weeks before also, the same, because this is the time the reservoir, Samanlava reservoir has been lowered for the lowermost levels, sinkhole number 1. So when it reach these levels of the sandbags, water will diminish, so that all the water will go into the sinkhole. These are some of the sinkholes which we have investigated for potential rates of infiltration and so on. Also, some dye tests have been carried out to identify to see whether this dye water, leakage water with dye is coming out from the main leak or some other piezometric valves and so on. But unfortunately, this dye could not be detected because these are dilute. These should be diluted within a vast area, so that the concentration of this dye is so less that it cannot be detected. These are some of the geological cross-sections made. So this is the grout curtain, and certain rock bands have been displaced by very prominent fault zones. And as a remedial measure, actually they have not identified, they have not considered the adit G ingress, but some ingresses along the riverbed have been considered, so that they have dumped clay when the reservoir is filled. So that is called wet blanketing. Usually these bottom open barges, or the clay is dumped into the bottom open barges and brought into the place and just open it as a lump. All the clay is supposed to be reach the reservoir bottom and seal the existing cracks and so on. So this is the way the divers were deployed to do the dye test just in front of the adit G portal, and very successful results have been obtained that whatever the dye inserted into the adit never comes out. So there is a considerable flow in towards the adit, so that it can be concluded that water going into the right bank. And also to confirm it, we have constructed two core drilling here. So in the right bank, usually reservoir level is at, when reservoir level is at this, so there is a gap of 25 meters for all the boreholes in the right bank. But these boreholes which have been drilled into the adit G, they showed the same water level as the reservoir level. So that is also a proof, another proof to say that water is leaking through this adit G. Right, that's about the Samanala, and then I'll move into the Umaoya headrace tunnel. Of course, some time back there had been big controversy, big problems of the whole country. Of course, when engineer Nihal Rupasinghe was the secretary to the Ministry of Environment and Mahaweli Development and Environment, of course. So, so we could join with the Umaoya project to do to find what can be done and so on. So when we talk about Umaoya, Umaoya is the river with the highest sedimentation rate. So this is a drone image taken just downstream of Ranthambwe Reservoir. Can see how water from Umaoya brings high amount of turbidity. So this Randanigala Dam is somewhere there, and Mahaweli water is not that much turbid. So here also you can see how much soil or sediments are being brought to Ranthambwe Reservoir. So it sweeps the agricultural lands in Bandarawala Velimada area and brings all these sediments into Ranthambwe Reservoir. So as it was estimated, 35 to 40% of Ranthambwe Reservoir is filled with sediments during the last 30 years. From time to time, of course, part of the sediments have been washed away by bottom open gates and so on. This Umaoya project, Umaoya development, multipurpose development project is constructed far upstream of the Ranthambwe, that is towards Bandarawala. From Bandarawala area, the water is brought to Vellava area through a 15-kilometer tunnel. So two dams have been built here, and 15-kilometer long tunnel brings water to the powerhouse at Vellava, very close to Vellava. So schematic diagram is two reservoirs are there. These two reservoirs are linked by a linked tunnel, and from there headrace tunnel, which is 4.5 meter diameter and 15-kilometer long, comes there, and vertical shaft of 600 meter brings the water up to the underground powerhouse. So it generates 120 megawatt of electricity, and water will be brought back to Kirindioya, which is through Alikotara Reservoir. So this is the Puhulpala Dam, one dam which is 50 meter high. Then this is Dairaba Dam, also 55 meter high. Headrace tunnel starts from there, and link tunnel. So this reservoir and the other Puhulpala Reservoir are being joined together by this link tunnel. So this is the link tunnel between. This is constructed by conventional drill and blast technique, whereas this headrace tunnel, 15-kilometer long headrace tunnel, was constructed for the first time in Sri Lanka by TBM, tunnel boring machines. So while drilling, excavation was going on, all of a sudden in 2014, one night of course, all of a sudden, huge water ingress came into the tunnel. So what happened was the people in the area, so they have used their dug wells to bring water, take water or draw water for their day-to-day use. But on the following day morning, when they put their buckets into those dug wells, they have found now water. So very quickly, water has been drained from those dug wells. So this is the tunnel boring machine that has been used for this TBM tunnel. So this is the cutter head. It is first that has been used. 2 such TBMs have been used, but now, of course, for Upper Alahara tunnel, they are using much bigger, about double the size TBMs. 2 TBMs are being used. So what happened actually in Umawe was, initially this 15-kilometer long tunnel is a straight tunnel. There are a lot of investigations have been done. For example, 13 boreholes have been drilled and investigations have been done. And these 13 boreholes indicated that there are highly pervious ground and some karstic cavities and so on within this area. So what they have done, actually that was a mistake from our government side. Of course, that contract has been given as EPC contract, EPC contract. So contractor has the freedom to do whatever it is and so on. So what they did was, they have just deviated the tunnel trace because they knew that this trace is impossible, or lot of problems. So they just simply deviated from this side about 250 meters from the original trace, but they have done nothing. No investigations have been done for the new trace without any boreholes. Although there have been 13 boreholes drilled for the original trace, no boreholes have been drilled, or no investigations, no geological mapping or anything has been done. So while the tunnel was progressing up to somewhere here, only that huge problem or huge disaster started. If the good rock, if the sound rock is there, it is only inward segment is done, concrete segment. No supports are necessary for the roof and walls. So this good rock or sound rock. But if the rock is not sound, or at least some partly weathered and so on, so concrete segments are erected. Inward concrete, left, right walls and roof segments. So these such TBM, the TBM coming into, TBM cutter head breaking into the powerhouse. So powerhouse cavern, that is the first tunnel made as tail race tunnel from powerhouse to bring the water from powerhouse to Alikotara and so on. So this is the powerhouse cavern, huge construction. So it is much below. This is the upper floor, of course. These generators are being fixed. The turbine is at about 2 or 3 floors below. So this is the turbine flow, and these turbines are, this is connected through the shaft to the generators. And water is brought along the initially low pressure tunnel, 15-kilometer long head race tunnel is a low pressure tunnel, then 600-meter shaft is being constructed. So that shaft was constructed by this race boring machine. So from the bottom it started and continued to construct. So this TBM backup is 200-meter long. That's why if something happened at the cutter head or the operating phase, treatments cannot be done until this 200-meter length is passed. So that's why most of the seepage problem, problem was aggravated, and until the entire area is drained, treatments could not be done. So these are the concrete segments, segment lining, inert lining, walls and roofs. break into 4 sets. So 2 locomotive tracks are there. So you can see here with fine fracture, you can see seepage at the. So after this expert panel's opinions and so on, so it has been advised to do a detailed geological mapping for the entire tunnel trace, 1 kilometer corridor. So that has been undertaken by the Department of Geology. So we did this 1 to 1000 scale mapping, and during that each and every outcrop and in the area have been investigated, and we could very accurately identify the existing structure and the geological formations and so on. So that all the existing lineaments have been encountered, so that we could accurately tell where will be the next leakage. So, for example, we have managed to, although at the beginning the British engineers and Iranian contractors, they didn't want to accept our ideas, but later on, once we gave the figures very accurately, for example, if we once we tell that the next leakage will be at the chainage of 855 chainage, sometimes 854 depth length, the leakage appeared. So after that, of course, they were extremely happy, and every time we were called there, and we had to give the predictions for the next sections and so on. So these are the several expert panels have been called for from various countries. So here, Professor Niviratna is also there. So we had to explain the geology over there, and so, for example, we know that at this location there will be another huge here. These are the faults. These red lines indicate the fault zones. So some drilling also have been conducted. So for example, this is the tunnel trace. So you can see these long lineaments, morphological lineaments are there. So definitely this lineament is a fault. So when it encounters the tunnel at here, there will be a huge leakage. So we could confirm it by geological mapping, surface geological mapping and the structural mapping. So that's how we could very accurately predict where will be the next leakage and approximately how much amount of water will leak and so on. Like this, and interestingly, this all the dried domestic wells are on a particular rock type called condylite, which is having deep weathering. So all the dug wells which are constructed on Chanokitic gneiss or any other rocks, they were not affected so fast. But the condylite has deep weathering because of its nature and so on. So out of these 240 dried domestic wells within the 500 meter from each side, most of them are from condylite rock. So here dried up domestic wells, these red dots indicate dried up domestic wells which are from the condylite area. So for this mapping, of course, Professor Pitawala, Professor Malaviyarachi, everybody joined, all the departmental staff, Professor Dharmagunandana and everybody. So it was very well correlated with the surface geology. So all the dug wells drilled in condylite rock became dry within a day, within 24 hours time, when it encounters the leak. All the houses, almost all the houses constructed on condylite rock have been cracked like that. That is also very remarkable. That has not happened to the houses that have been constructed on weathered overburden of Chanukitic gneiss also. So due to this rapid depletion of groundwater table, this effective stress increased and so on, so that these cracks, some of the houses have been totally abandoned. Not only that, along the ground there are large cracks spread all over the area. There are interestingly some sinkholes. Half of one house, half of this house is already went into the sinkhole. It is about 40-meter deep sinkhole. Nearby core drilling indicated that there is a huge, about 20-meter high cavity, cast cavity is there under 60-meter depth, so that these cavities must be collapsed when the water is drained into the tunnel. So there's another interesting thing that is on the Bandarawala-Badulla road. Very close to the Bandarawala-Badulla road, there is a lineament just by the side of the road. So we predicted that this would be a prominent fault zone, so that there will be definitely there will be another leakage. But unfortunately, the project engineers and so on, they didn't accept it at that time. They made a vertical drill hole and showed that, saying that, so it's a sharp, very good rock without any fractures and so on. So where is the so-called leak and so on, they were telling. But anyway, on the following day, when they really struck this lineament, which is a fault, they have encountered about 3 times bigger leakage than the original leakage. So here, initially, all the biggest disaster happened when the leakage was 400 liters per second, 450 liters per second in 2014, December 24. So later on, it was reduced gradually, and at this point, because they didn't pay much attention to that lineament, they could not tolerate this much of leak, that is 1,300 liters per second. So immediately they had to stop all the excavations, and they had to modify the TBM to cope with some probe holes and pre-grouting, so-called pre-grouting. Some probe holes are to be drilled and cement grouted, so that all the fractures are filled with cement and can proceed the construction. So that has happened from there onwards. So these so-called pre-excavation grouting, TBM tunnel boring machine tunnel head is here. These probe holes can be drilled like that. So up to about several meters, 34 meters or so. So after drilling all over the radially, these drill holes are to be drilled. So all these are grouted with high pressure cement water mixture, so that the ground will be stabilized, so that easily this. But obviously, this make this tunnel progress much slower. So for that, this contractor didn't like much. But this is the way the surrounding of the tunnel is to be grouted as up to about 4-meter grout radius. So this is how this fracture, natural fracture, open fracture is filled with grouted cement, grout material. So there's another incident that Professor Dharmagunandan and myself, we have identified another location of potential seepage, potential leakage or potential weak zone, so that we have carried out resistivity survey, resistivity profiling and so on, so that we identified that weak zone that shown by this blue color extends even below the 60-meter depth. So tunnel is at about 60-70 meter depth at this particular location. So we could accurately predict that 800 plus this chainage would be the possible deep extending weak zone, and there will be seepage and so on. So with 1 meter accuracy, we were correct. So it was there, but fortunately, because the predictions were taken into consideration, they could manage without much difficulty. So even under 400 meter depth, even at 400 meter depth, such weathered zones exist along discontinuities, folds, joints and foliations. So they get weathered, and here you can see at 400 meter depth. So these folds with water-bearing folds with groundwater flow. So you can see precipitations and so on. So all this happens. While studying all this, we could conclude that this is the place where they have done the mistake. So while they have deviated the original or studied the tunnel trace, they have done nothing. No appropriate investigations have been done for this deviated trace. So the condition would have been much worse than the original road. So deeply weathered rock, condylite, karstic ground, identified in 13 boreholes along this. So instead of, they have selected this one, but this had been much worse. Okay, with that, we'll conclude that Umawe study, and we'll move into Kandy Tunnel investigations done for the Engineering Design Center, and we as geologists join from the Department of Geology. So this was the original proposal to have bypass tunnel from west to east without going through Kandy city. So this is the cross section of the area, and here we can see relatively less cover, and in the tunnel 2. So starting from very close to hospital area, Kandy hospital area, and so geological mapping has been carried out as we have got experiences from Umawe and other projects. So we could do this very intensive geological mapping at 1 to 1000 scale along the tunnel trace, 1 kilometer corridor, so that we could identify each and every lineaments or potential fault zones here like this, so that some faults, if a fault is, if the tunnel is crossing a particular fault at right angle or perpendicular to the fault zone, so it is the minimum damage, of course, so that we can proceed with suitable mitigation measures. If this tunnel is aligned almost subparallel to these lineaments, then treatments would be really difficult. So that this tunnel 2 has been identified as, this section was identified, actually IFS, National Institute of Fundamental Studies is there somewhere here, just below IFS. So this area is severely actually vulnerable for potential seepages and so on. So these boreholes, KT5, KT8, KT9, they have been drilled, they have been designed to identify the rock conditions at the tunnel depth, so that most of them were angle drill holes. They could, they correctly, exactly showed the existence of these faults as we predicted. So, for example, this KT10 indicates this fault, existence of this fault at the tunnel depth, 9, 11, all these. So this is the way drilling has been carried out, deep drilling up to about 250 meters at some locations. So here you can see, we could see faults, siliconsites or myelonites, which were as expected. So these are textbook type examples for faults, so that we can accurately tell that this area is can be subjected to problems, but so that if proper mitigation measures are adopted, tunnel can be constructed. For example, like this, right? So along the cross section, so this red indicates the lineaments and weak zones, red areas. So these are the areas we have to be very careful while tunnel is being excavated. So here, similar to Umaoya, we could manage to, with the experience we got from Umaoya, we could accurately estimate these, but it has been proven through these angle holes or boring. Here, so this area is particularly a very shallow area, so that actually in the first stage of our study, this tunnel 2 was considered as a bit tricky. So instead of that, we could propose another tunnel, not going through there, but not going through Bogambara and so on, going away from that, which will have very less impacts, going under the Dunumandalawa forest area. Yes, that's all. Actually, due to the time, I think that's all I can show, although I have another set of dams and tunnels, and the results that we have got. For example, Norton Bridge Reservoir had a huge leakage, so that we managed to find the leakage, location of ingress, and we could propose how it can be closed, how it can be sealed, and so on. And in Mausakale Dam, there was a small seepage which can go as a piping and so on, but that also could be effectively identified using dye techniques and so on. Likewise, thank you very much.
It was truly an inspirational talk and indeed a story of motivation for the young geologists for geological adventures. Thank you once again. On behalf of the Geological Society of Sri Lanka, we really admire your speech. This brings us to the end of the event. Dr. Titus Kure, the Secretary of Geological Society of Sri Lanka, will now bring the vote of thanks.
Dr. Upul Premaratna, and today Ananda Coomaraswamy Medal recipient Dr. Jagath Gunatilake, and the nominator for the today Professor Ananda Balasuriya, and all the GSSL past medal recipient and GSSL members, and the esteemed guest today. I am not going to mention you by name. So we have come to an end of an event where we gathered here to recognize the geologists who have contributed immensely to the Sri Lankan geology by following the Ananda Coomaraswamy's legend. And first and foremost, I would like to thank all of you who have gathered here to witness this event. And most of you have sacrificed your time just to witness this, witness the success of the geologists who have celebrated today. And also I would like to thank the people who have joined with us online by Zoom as well as Facebook. And also I would like to thank for the Director PGIS, Professor Peter Weller, and the Board of Studies Chairman of Earth Science, Professor Nanda Balasuriya, for helping with us for making the arrangement for today's event. And without your contribution, we could not make this a success. And also, I would like to thank all the individuals who help us for the today's event by various support, especially PGIS staff and the Department of Geology staff, and all undergraduates, postgraduate, as well as demonstrators of the Department of Geology. Your volunteer time and efforts have made success for this event. And if I were unable to mention any of you by name or by your support, and at the end I would like to thank all of you for all of your cooperation to make this event a success, and thank you very much.
You all to a refreshment in the cafeteria in the second floor of the PGIS, and wish you all a very pleasant evening. Thank you.